Okay, great. So I just need the stream. Oops. Okay, let them through.
Okay.
Oh, who's that guy? Hold on. Where's the mute button? Why?
Okay, I've successfully muted everyone, but now I need to make sure that Syed, you have the ability to unmute yourself? Okay, good.
Yes.
Okay, great. Hi, everyone. Okay, so at the top of the chat, I'm hoping that everyone can see the YouTube stream link. That's our backup in case Zoom fails. And also, if there's someone who's struggling to get into this class, please forward it to them. Okay, it's 11:10, so let's get started. Okay, a slightly different instructions for today. If you have a question, you have to do two things. You have to raise your hand using the emoji or the feature inside the participants list. And then you also have to write your question so that Syed can read it. That way he'll send you to the main class if your question hasn't been answered already. But if it's answered already, then he'll just answer it for you, or your classmates will do so. So if you have a question, raise your hand and type it out. Okay, so I'm going to ask for questions in a moment, but while people are streaming in, let me just do a quick review of what we did last time. Last time I introduced sets. Okay, so a set is I think everyone understands what it is. It's a collection of elements, and that collection is viewed as an object in its own right. So we give it a name typically, like here I've given it the name S for the set containing the element X. And so there's a bunch of different examples. We talked about finite sets, the cardinality or size of a set. And then we had this idea of maps. So the maps, as you can see, this is the domain set. This is the codomain set. And every member of the domain is sent somewhere, is sent to a specific value. Okay, and we usually denote that with this notation, that an element is sent to f of x, but the map has the name f. Okay, so when you see this diagram, this picture of x arrow y with an f on it, you should think that this is explaining everything that there is to know. I mean, this symbolizes everything that is encoded in the map f. It's telling you what its domain is. It's telling you what its codomain is. And then in this arrow is all of the really important information about exactly how are the elements in X sent to the elements of Y. So the details of what's happening inside this arrow are very important. For example, here, if I have R, G, and B, and if I have all of the colors from 0 to 255, right, I'm not yet telling you what the values of R, G, and B are, right? The domain is specified, the codomain is specified, but the information of exactly what is assigned to R, G, and B has yet to be determined. And that's what this information, the information contained in this arrow, consists of. It's telling you exactly, where R, G, and B are sent. These maps are sometimes called functions, but I prefer to reserve, and this is something that many people do, many mathematicians do, is to reserve the term function for maps where the codomain is a number, some kind of numbers, okay? That way functions, they take numerical values, whereas maps, they could be maps, from books to people, or cars to driveways, or it does not have to be anything to do with number. Okay, so any questions about that, or any general questions just to start us off, please ask them now.
So Jay, you have a question?
Yeah, sorry, I was just still writing it out in the chat. Should I ask it and then?
Go ask.
Okay. So when so this is relating to what we just said, or what you just said. For the problems in the assignment for next week, should we treat all of the maps and sets as if they can be numerical and non-numerical, like if there's inverses, inverse maps, or because I don't know if that applies to non-numerical maps.
The statement of the problems on the assignment is carefully done. So there's no need for, that's a very good question. So see, what he's asking is the following. So, if you have a function, let's say f of x is equal to x, where x is in x, okay, sorry, let me just set my tablet in a better location here. So suppose that we have a function from R to R, okay, and it's given by x goes to x plus 1, okay? Then if I asked you what the inverse of this function is, many people here would probably say that it's the function g, which goes from R to R, which takes x and sends it to 1 over x plus 1. Okay, and the reason that you might call this an inverse is that when you multiply the value of this function by the value of this function, you get 1, which is the multiplicative unit in the numbers. So this is giving the inverse in the sense of multiplication of numbers that this function gives. But these are not inverse maps. Okay, inverse means that if you take x and map it here to x plus 1, right? The inverse would be the opposite, the map that goes in the opposite direction, which undoes the process that the first map did, okay? And that would be the function that takes y and sends it to y minus 1. X, the function f, let's say I'll call this one f and I'll call this one g. The function f adds 1 to your number, and the function g subtracts 1 from the number. And so if you compose f and g, if you do f and then g, you end up doing nothing. That's what an inverse is. Inverses have nothing to do with multiplication in number systems. And they also have nothing to do with addition in number systems. I just gave this as an example. Okay, so so there are no hidden assumptions in the assignment questions, to answer your question.
Okay.
Any other questions?
Yeah, so Harsh has a question.
Go ahead.
I just wanted to know, why is it that for the definition of a function is that one value in the domain can only correspond to one value in the codomain? So why isn't a circle considered a function?
Why isn't what?
Why isn't a circle, an equation for a circle, considered a function?
Well, okay. So a map is a fundamental object. Okay, there's many fundamental objects. Okay, so you may have preferences about which object you like to study. Okay, but the most fundamental object is a map of sets, and it relates one set to another, and it takes everything in the domain and sends it somewhere in the codomain. That's what we call a map. Okay, it's better not to ask why. Okay, just wait and you'll see all of the utility that we get out of it. Okay, but the important thing is really to understand what it is. You could have imagined that there are other things which are called relations, which are not maps. And actually, the equation for a circle is the zero value of a map. So it is indeed a map, despite what you said. And anyway, I'll bring that in as an example later. Okay, so
So
let's just pause for question. Let's pause the questions for now, and let's go on. I want to present a little bit more material. Okay, so so let's say we have a map from the domain X to the codomain Y. Okay, there's a few different special cases of maps which are they appear all the time, and so they're important to know. One is called injective. Okay, so an injective map, okay, what it means is that you do not have value collisions. So in other words, you cannot have two different elements of the domain which are mapped to the same element of the codomain. Okay, no collision of value. So injective means that when, sorry, let me just move the photos. So different inputs result in different outputs. Okay, so let me write that in mathematical notation. Okay, so if x1 is different from x2, then f of x1 is different from f of x2. Okay, so we have no collision of outputs. Okay, so let me maybe draw a picture. Okay, so in other words, so this is forbidden. You cannot have two values going to the same point, 2 points being sent to the same point. So when you guys send emails to all of us, you typically send it to me. So this is non-injective. In order to have an injective email, it would have to be so that everyone in the class would send an email to a different person. Okay. Another case is surjective. Okay. And this is when all possible outputs are achieved. Okay. So in other words, for every point in the codomain, there exists at least one point in the domain. There exists some point in the domain such that f of x is equal to y. So that value is taken on by some element in the domain. Okay, so typically what that would look like is, we don't even have to draw the domain. the point is that okay, we may not know. I don't need to draw what's happening in the domain, but everything in the codomain is achieved. Okay, and then bijection or bijective. So this is this. If it's injective, then F would be called an injection. If it's surjective, it would be called a surjection. And if it's bijective, then F would be called a bijection. Okay, if it's so bijective means that both hold. So it's both injective and surjective. Okay, and so right. So if I wanted to describe a bijection between x and y, let's say between x and y, then no child is left behind. So every member of the domain must be sent somewhere. Okay. The next one cannot be sent here because that would ruin injectivity. So this is not possible. Okay. In order to maintain injectivity, I need to make sure that it's sent somewhere else, somewhere different from where the first point was sent. Then there, as you can see here, there would be no additional choice for where the third one should go. It would have to go there. So, and now that we see that all possible values are taken, this would be an example of a bijection. Okay. Similarly, suppose that all I was interested in was a surjection, was an injection, right? Then, again, you're not allowed having, this is not permitted for an injection. Okay, every point must be sent somewhere different. Okay, so this is an injection, but not a surjection. Okay, and on the other hand, if I was interested in a surjection, that's fairly easy to produce. This would be an example of a surjection, but not injective. Okay, anytime that you see convergence or collision of the arrows, that's indicating that we do not have an injection. Okay. So let's say, just to give you another example, suppose that I wanted to understand bijections from the set 1, 2, 3 to the set 1, 2, 3. Okay, now I don't want you to get confused here or really, the particular numbers that are in this set are totally irrelevant. The important thing is that there are three distinct elements in the sets. So the domain and the codomain have cardinality 3. Okay, and so what I'll do is I'll just draw pictures of them. I'll draw pictures of them. Well, I'll just draw 1, 2, 3 and 1, 2, 3. Okay. Okay, and so what are the possible bijections between these two sets of cardinality 3? Okay, so the simplest given the way that I've labeled the elements of the sets, the simplest possible map is the one that sends 1 to 1, 2 to 2, and 3 to 3. Okay. So that is a bijection. There's no collision of outputs, and all outputs are achieved. And so this is a bijection. And this is a very special bijection, which is called the identity map. Okay, and this special bijection exists whenever the domain and the codomain are the same set. Whenever the domain and the codomain are the same set, it is possible to do this. It's possible to say, where do I send 1? Well, just send it to 1. Okay, it's an obvious choice of map, which wouldn't be available to you if the codomain were different from the domain, because there wouldn't be, if I had written instead of this, instead of 1, 2, 3, if I had put 4, 5, and 6, the two sets would be different sets, and so it wouldn't be clear what I should send 1 to, if there would be no identity map. Okay, but there's other possibilities. So instead of sending 1 to 1, I could just send 1 to 2. Then where should I send 2? I could send it to 3 and 3 to 1. Okay, this would be another example of a bijection. If I stick to my guns and I keep sending 1 to 2, right? Then maybe I should change my decision about the further elements. So where should 2 be sent? Instead of sending it to 3, I could send it to 1, and then 3 has to be sent to 3. Okay, and those take care of all of the cases where 1 is sent to 2. Actually, let me move this guy over here, because I should have continued. I should have listed all the ones where 1 is sent to 1. So let's say I stick to my guns and send 1 to 1. 2 could have been sent to 3, and then 3 would have to be sent to 2. Okay, so these are the two possibilities where 1 is sent to 1. Now, assuming that we've gotten all those, the other possibility is that 1 could be sent to 2, and in that case, then 2 could be sent to 1 or to 3, and those are those two possibilities. And finally, 1 could have been sent to 3 instead, and then 2 to 1 and 3 to 2, or 1 could be sent to 3, 2 could be sent to 2, and 3 could be sent to 1. Okay, so these are the 6 possible bijections from 1, 2, 3 to itself. Okay, all of these are maps. They are different maps, but they have the same domain and codomain. Okay, any question about this this example?
So Abdul has a question.
Yeah, go ahead.
Yeah, so I was just wondering what this flipped A means and the inverted E, the ones you wrote, like, can you scroll up, please? A little bit more.
I think it's on the page previous to this one. Yeah, below the second last page.
This one,
Yeah.
or this one? Can you just ask your question again, please?
Yeah, I was asking what does the flipped E or the inverted
Did
E?
you watch the first lecture?
Yes, I did.
Because it was explained. It was explained there. This is the symbol that means X is an element of S. X is an element of the set S.
Yeah.
Right? R is an element of the set P. G is an element of the set P and B as well. So this is explaining the fact that this is an element inside the set S. It's contained in S. Anything else?
Thanks. No, thanks.
Anyone else about
And then
this?
Jay, I think Jay has a question.
Yes.
ahead.
Sorry. I think he was referring to.
Don't worry about what the other questions are. I'm trying to get away from that question because that question is about last lecture. I want to talk about maps and bijections and injections. So let's
no, because I think it was from this lecture. I think he was referring to something else. That right there in the surjective where you wrote A, for all A and Y, there exists.
Oh, okay. Thank you. Sorry. You're right. So I was trying to give you a logical or a mathematical way of writing the sentence above. So for all, that's what this means. I think 357, 157 usually is doing this, but this is for all. And this is there exists. Okay. So for all y in the domain in the codomain, there exists an element x in the domain such that f of x is equal to y. Okay. Sorry about that. I was getting annoyed because you weren't listening to the first talk. Anyone else?
Yeah, so Shashvat has a question.
Go ahead.
I had a question about the identity map. So you said that the two sets, the domain and the codomain, must be identical, but also shouldn't it be like, the elements correspond to each other? Because like in the other 5, they don't. I just wanted to make sure.
Yeah, let me just write that out. So when the domain is equal to the codomain, i.e. f is a map from x to x, there is a natural or a specific map called the identity map. Okay, IDX, or sometimes called IX. There's many names for the identity map. And the identity map, what does it do? It takes any point and sends it to itself. This is for all x in the domain. Okay, so anytime you're considering maps from a set to itself, there is a specific map among all maps, which is this one, the identity map, the map that does nothing. I mean, it actually does something. It just doesn't move things around at all. It just sends each point to itself. Okay. You can send emails to yourself. Sometimes people do that in order to keep notes. Okay, anyone else?
Yeah. So Hongbo has a question.
Go ahead.
Hi, sir.
Hi.
Sir, do you list all of the possible bijection, or this is only 6 injective bijection?
And so I went through them one by one in order to explain that there are all of them, actually, because you see that one must be sent somewhere, right? That's a map. It has to be sent somewhere. So where can it be sent? It can either be sent to 1, 2, or 3. So I said, let's say 1 is sent to 1, then what about 2? Where is it sent? It can be sent either to 2 or to 3. And then I'm done.
Yeah, can I say 1 send to 1, 2 send to 1, and 3 send to 2?
Okay, so if 1 is sent to 1 and 2 is sent to 1, then that means we have a collision of values. That means we have 2 different points being sent to the same point.
Yeah.
Okay. This is not permitted in injective. Injective means that does not happen.
Okay. But is bijection?
Bijection means both injective and surjective.
Okay, I got it.
Okay. Okay, next concept, important, super important. This is the last piece of the definition of sets. So composition of maps. Okay, so the composition. So this is a definition of the concept of the composition of maps. So the composition of F and G, okay, which is defined only if the codomain of F is equal to the domain of G. Okay, and I'll highlight this, and I'll highlight the codomain of F and the domain of G. You can see that they are the same set. They have the same name, Y. Okay, so if F maps X to Y and G maps Y to Z, right, then you can think of Y as being an intermediate space, right? That we're starting with X, we're mapping everything in X to Y, and then we're mapping everything in Y to Z. So if we do both properties, if we do both maps, sorry, if we apply the map F and then apply the map G, it will be going from X to Z. So it will bypass the intermediate set Y. So the composition is a map G circle F, okay, and it goes from the domain of F to the codomain of G, yeah, which takes X to just G of F of X. Okay, so let me draw a picture. So we have X, we have F going to Y, and then Y to Z given by G. Okay, I'm going to put these above. And then the composition, which is called F. So it's always a little bit annoying because you have to reverse the order like this. Okay, this is the composition. Okay, so this is a really, really fundamental property of maps, of sets, is that they have a composition. They can be composed, okay? And let me just give some examples. Okay, suppose that we have suppose we have X, Y, and Z. Okay, and suppose that we have some map F. F. And suppose that we give another map G. Okay, so you see that everything in X has been sent somewhere, and everything in Y has been sent somewhere by G. Okay, and so what would happen if we compose these maps? Well, what you need to do is kind of look at each point in the domain at the very start, right? Where does this get sent? It gets sent here by F, and then by G it would be sent here. So in the composite, Okay, in the composite, I would get that this point would be sent here. This is by F composed with G. Okay, on the other hand, this point is sent up here, and G sends that here. And so this means that this would also be sent here. And finally, this point is sent here, and this point is sent here by G. And so we would get that this point is sent here. Okay, and this, I hope it's clear, this is what I meant, X and Z. So we have F, we have G, and then we have F composed G, like this. Okay, and in the assignment, I asked you to show a very easy but very important fact, which is to show that composition is associative. Okay, meaning that for maps of the form like this, if I have 4 sets and I have F, G, and H being successive maps, what I want to show is that if I compose F and G first, and then I compose with H, okay, this would be the same thing. This is the same map as if I were to compose G and H first and compose that with F. Okay, so this is the all-important associativity condition, which is satisfied by composition of maps. Okay, and so at this point, I don't want to make a big deal out of this, but let me just state it. So at this point, we have sets, we have maps between sets, and we have composition of maps. Okay, so we have sets, maps, and composition, and that is a completion of the playground of sets, right? In order to play on the playground of sets, in order to work on the sport of sets, okay, you need to know what the sets are, you need to know what the maps are, and you need to know how to compose the maps. Okay, and that's a complete system. And what mathematicians call this is a category. So this, I'll try to write it small so that it doesn't intimidate you. This defines the category of sets. Okay. So it is a kind of universal language where we can do a lot with these data. Okay, I'm going to open it up to questions now.
All right, so Yuchi has a question.
Go ahead.
Yes, I want to ask if there is a set X to a set Y, is all elements in X have a map to elements in Y?
So I think what you're asking is it true that every element in the domain must be sent somewhere? Is that what you're asking?
Yes.
Yeah. So that is what a map is. No child is left behind. Every element of the set, the domain set, must be sent somewhere.
Okay. Okay.
It's like, you know, a map is, it's like painting a room. Okay. If you're a proper painter, you will not leave one of the walls unpainted. If you're going to paint, you paint. You paint all the walls. You don't just leave one unpainted. So painting is an association. For every wall, you associate a color. So that's a map from the walls to the space of colors. So painting is a map, and a painter is quite literally the map.
Okay, thank you.
Of course, you could have an incompetent painter who doesn't paint one of the walls, but that would not be considered a proper painter, and it would not be considered a map. Any other questions?
So Charlie has a question.
Go ahead.
Okay, sorry, can you hear me?
Yes, go ahead.
Okay, just about the notation. Does G circle F mean the same thing as F circle G? Or is it G?
No.
Okay.
Because you see, in order to be able to do this, in order to be able to compose F to do G circle F, what it means, the reason why, like, notice here, I have F and I have G, but I reverse the order here, G, F. Why is that? The reason is because first we apply F and then we apply G. And so it looks like this. You see that G appears first and then F.
Okay.
Now,
makes sense.
Because F goes from X to Y and G goes from Y to Z, it is possible to do F first and then G. But I cannot do G first and then F because the domain of F is X, you see? So even if I wanted to, I wouldn't be able to apply G and then apply F because F doesn't act on Z.
Right, okay.
So composition, you have to be very careful that the order matters. And in fact, it may be that it's defined in one order and not defined in the other order.
Okay, it's just tricky because you have to read from right to left instead of left to right.
Yes, so yeah. So if I wanted to deliberately confuse you, so deliberate confusion, okay, this would be confusing to those members of the audience whose languages are written from left to right. But if you write from right to left, you're in much better shape, because if I had a map, if I drew my maps the other way, which I certainly could, there's nothing wrong, there's nothing preventing me from drawing my diagram in the other direction. The arrows are still pointing from the same space to the, you see, I'm going from X to Y and Y to Z. So here I go from X to Y and Y to Z. I've just rotated the diagram. But now the nice thing is that when I write the composition, it is in the correct order.
Okay.
Just because of the fact that we wrote it in that way. So some people insist on writing all their maps this way. So purists would draw their maps this way.
Yeah.
Okay.
All right.
Any other questions?
So Gal has a question.
Go ahead.
Hi, sorry. I just wanted to ask, so when you were showing the associativity of the maps,
Yes.
right, that first of all, that neglects the first map, right? It still has to be in the first position, F. Otherwise, our domain is different. Like F can't be moved around, right? Usually when we mean associative, you can move everything.
I'm not understanding your question.
Like when we say, let's say associativity for like multiplication,
Yeah.
if you have 2 times 3 times 4, you could
Yeah.
have any of them in either of the positions, right? But for maps, F still has to remain in position 1. Otherwise, it's not our domain, right? Our original domain.
Yeah, I mean, if you start writing like 2 times 3 times 4 is equal to 3 times 2 times 4 is equal to 4 times 2 times 3. Okay, that's not the associative law. Associative law is only this. You're using the commutative law as well.
Oh, my apologies.
This is the associative law. It means that if you bracket them in 2 different ways, it gives the same result.
Okay, I heard associative used for that as well. So I see that's wrong.
This is the associative law, yeah.
Okay, and then for when we're talking about composition, so if you're allowed to do them in either order, that means that if we map from G to H, right? Or we, from the domain of G to the codomain of H, then we start from F and make it all the way to the end. It's the same as kind of doing it the other way around, going from F to G and then G to H.
Sorry, it's too complicated,
I know it's kind of a rephrase.
So if you have a map from X to Y, okay, and you have another map from Y to X, this is a very special case, right? It's not a general case like this where F, G, and H are just mapping between 4 different sets. Here we have only 2 sets involved, okay? So in this special case, F compose G, what does this mean? This means that we start at X, we go to Y, and then we go to X. We first apply F, and then we apply G. Okay, but in this special case, it is possible to do them in the opposite order, because that would start at Y, and it would go to X using G, and then it would go using F back to Y. Okay, so this composition, let me draw it like this. So G composed F is like this. G composed F is a map from X to itself. Okay, and F composed G is a map from Y to itself. So you see that when you compose, first of all, you can't usually compose in 2 different directions, in 2 different orders, right? Usually only one of the compositions is defined, like here, first F, then G. You cannot do first G, then F. That's impossible for these sets. But in this particular case, it is possible to do F and then G, or to do G and then F. Those are 2 possible computations, but they give completely different types of maps. One of them gives a map from X to itself, and the other one gives a map from Y to itself.
Okay, thank you.
Okay, let me leave it at that for now, and do one last thing before we take a break, and that is to talk about inverses of maps. Okay, so inverses, the inverse of a map Fx to Y is by definition, okay, a map G going the opposite way, which undoes what F has done, such that 2 conditions hold. First of all, if I compose them in one direction, so this would mean first you start with X, then you go to Y, then you go back to X. Okay, so if you go from X to Y and then back, this should be the identity map on X. Okay, this is another way of saying that if you take a point, send it by F, and then send it back by G, you've done nothing. You've sent X back to itself, and that is known as the identity map. Okay. On the other hand, if you can compose them in the other direction, like I said, and what you should get is the identity map on Y. Okay. So a map may not have an inverse. Okay, this is a warning that it is not at all clear that an inverse should exist. Okay, but if it does exist, we call it F inverse. Okay, it's like F to the power -1. Okay, which might be a confusing notation. It has nothing to do, this has nothing whatsoever to do with like 1 over F, which doesn't even make sense. Okay, this has no relation to that at all. The point is that it's the inverse map. It does the opposite of the machine. It's like the reverse engineering of the engineering map F. Okay. So, for example, maps that have inverses these are perfect examples of maps that have inverses. Okay, inverses just mean follow the arrows going backwards. That's what it means, right? So if I wanted the inverse of this map, I would just take 1 to 1, 2 to 2, and 3 to 3, following the arrows backwards. And what you can see is that that map is just another copy of the identity map. So the inverse of the identity map is, no surprise, the identity map itself. Okay. On the other hand, for this one, right, if what the map does is send 1 to 1, 2 to 3, and 3 to 2, then the inverse would take 1 to 1, 2 to 3, and 3 to 2, which is again the same as this map. So this map is self-inverse. Okay, now let's look at this map. Okay, this map takes 1 to 2, 2 to 3, and 3 to 1. And if I go backwards, it'll take 1 to 3, 2 to 1, and 3 to 2. So 1 is being sent to 3. So that's different from this map, the original map, right? So let me grab this one. I'll bring it over here. Okay. This, I'll call this F. This has inverse. I'll call it F inverse. And it takes 1 to 3, okay, 2 to 1, and 3 to 2. Okay, and if I rewrite this in the standard way, if I write the domain on the left, I mean, and the codomain on the right, then it takes 1 to 3. I'm just rewriting it, but I'm rewriting it flipped over so that the domain occurs on the left side and the arrows are pointing to the right. Okay, 2 is sent to 1, and 3 is sent to 2. Okay, so this is a picture of F inverse. Okay, and actually, it's useful to put them right next to each other, because then you can check. You can see 1 is sent to 2, and then 2 is sent to 1. So that 1 is eventually sent to 1. When I compose, I'm just going to get 1 is sent to 1. Okay, on the other hand, 2 is sent to 3, and 3 is sent to 2. So as you can see, we get the identity map by composing. And similarly, 3 is sent to 1, and 1 is sent to 3. Okay, and this happens in both orders, right? So if I take this and compose it this way, right, then you see that it's also true that 1 is sent to 3 is sent to 1. So I get the identity map 2 and 3. Okay, so that's verifying these two conditions, that we've found a map, which I gave the name F inverse, such that when I compose it with F on the left or on the right, I get the identity maps. So that proves that this map is the inverse of this map. Now, these maps are not the same. They look obviously different. You can see 1 is sent to 3, 1 is sent to 2, right? But if I look at this F inverse is also a bijection. So it must be in the list somewhere, because I listed all of the bijections. So here's this is the map that I called F, and the inverse must be here somewhere, and it's right there. So this map and this map, they are inverse to each other. Okay, you can just see they're put next to each other. So 1 is sent to 2, 2 is sent to 1. Okay. Similarly, if I ask, so this one is the inverse of itself, this one is the inverse of itself, and this one is the inverse of itself, and this one is the inverse of itself. So all of these 4 maps, they have the special property that if you compose them with themselves, you get the identity. Just composed with itself is the identity. But this one is not like that. This one, if you compose it with itself, you will not get the identity. But if you compose it with this one, you get the identity. Okay? So I'm just giving you a whole bunch of examples. This is not organized. The organized stuff is I wrote it all out. This, I'm just giving you a bunch of example information. Okay, now the last thing that I want to say before the break is that the bijections from a set X to itself, let me call it bijections from X to itself, are very special. Is a very special set of maps. Okay, so number 1, any pair, any 2 of them may be composed to give a third. Okay, and so this gives an associative multiplication on the set of maps. Okay, and number 2, the set of bijections from X to X contains a special element, the identity map, okay, which acts as a multiplicative identity. Okay, by which I mean that if you multiply it against anything else, by which I mean if you compose it against any other bijection, you're going to get that bijection back again. So composing with the identity is doing nothing to your bijection. And the third thing is that every bijection has an inverse. Every bijection, every element in the set of bijections from X to itself has an inverse. And that's in the assignment. Okay, this shows that if I consider the set of bijections from X to itself, and if I include the composition multiplication law, so composition, and if I include this this identity element, this is a list. Okay, it's a list that has, well, it's, I just want to explain that if I consider this set of maps together with this composition and together with this special element, which is the identity, this is called a group. Called SX. The permutations or symmetries of the set X. Okay, so this is what's called, we're not going to spend a lot of time in this class talking about groups. You will learn more about them in other classes, but this is an example of a group. Anytime you have a set with a composition law, with a composition operation, which allows you to multiply any two elements of the set, and in such a way that that every element has an inverse and that we have an identity element. That's called a group. And in this case, you can see that these are called symmetries or permutations, because what these things are doing is they're taking the elements in X and they're just moving them around. They're rearranging them in some way, right? Like you can see here, right? 1 is sent to 3, 2 is sent to 1, 3 is sent to 2. So that's a permutation of the three elements, 1, 2, and 3. Okay. Yeah, symmetry. So you could think that these are symmetries in the sense that they take the elements of the set X, they move them around, and the set X is still, is unchanged. It's still the set X. It's just that you've taken the elements and moved them around. You've sent elements to different elements. Okay, so so I want to take a break. So we're gonna start again at 12:20. So let's start again at 12:20. I don't mind. Usually I'll take breaks where I'm not going to talk, but if you want to ask questions, you should go ahead.
Okay, so
but feel free to take a break. You can always listen to the questions after. Actually, no, let's actually have it proper. We have to have a break. Apparently, otherwise you'll get Zoom fatigue and people will start dropping dead. So we will have a break starting now. We're going to come back in 10 minutes. Okay. Any questions?
So Dixshant has a question.
Yeah, go ahead.
Right. Thank you. I have a question I have two questions in the last two statements you have written. One of them being that you said that any two of them may be composed to give a third, and that's an associative multiplicative identity. Could you give an example in terms of the 1, 2, 3 set mapping to 1, 2, 3 set we did over there for clarification of what you meant?
All that I mean is that if you take any, these are all the bijections from 1, 2, 3 to 1, 2, 3. So there are 6 of them. Okay. So there are 6 maps, 6 bijections from this set to itself. Okay. Now, if I take any pair, any two of them, this one and this one, suppose. Okay. Then I can, right? So if I take any pair of them, I'll pick that one and this one, say. Oops. Take any pair. I can put them one next to the other, right? And I can compose them. So if I compose them, what will I get? 1, 2, 3, 1, 2, 3. 1 is sent to 2 by the first map, then 2 is sent to 2. So 1 is sent to 2 if I do both. F and G, and here I'm drawing F compose G, right? And then 2 is sent to 3, 3 is sent to 1, so I get this. And 3 is sent to 1, 1 is sent to 3. Okay, so I just picked 2 of them at random, and I can compose them. F compose G, and I get this. And if you look at this, you can probably see that it is here somewhere. It's right here. So I defined, by doing this composition, I defined a multiplication, right? Where I took this guy, this element, these two, I composed them together, and what did I get? I got this one. So you see that the elements of this 6-element set, this cardinality 6 set, they have a multiplication that is defined on them, right? So that if I take any pair, I can combine them, and I get a third. Okay, and then besides that, it has to have a multiplicative identity. There has to be an element inside the set. There has to be an element inside the bijections, right, which can be composed, but it doesn't do anything to the element. So in other words, if I look at the identity map, if I compose this with anything else, I'm just going to get that thing back again. So this composed with this, the first map composed with the second map gives the second map. The first map composed with the third map gives the third map. You see, here these two compose to give this map, but this one, if I compose it with anything, it will do nothing. It will just leave that map alone. That's what I'm talking about.
Right, that clarifies it. And also, this in the third bullet point, you said that every element in the bijection has an inverse. Do you mean every map has an inverse, or every element has an inverse?
Every element of the set of bijections. So what is an element of the set of bijections? This is a set whose elements are bijections, maps. The elements of this set are maps.
Okay.
So every map in this set has an inverse map.
Right, I understand. Thank you.
Okay. Okay, let's move on. Okay, so let's see. Okay, so I want to talk a little bit about how to construct new sets from old sets. Okay, so there's a bunch of different operations, very useful operations, which appear all over mathematics, which can be used to take two sets or take a set and modify it in some way. So the first one that I want to discuss is the notion of subsets. So given a set Y, a subset X inside Y is a set made of a selection of some of the objects inside Y. Okay, you have to, it comprises some of the elements of Y. Okay, so we can think of X as the elements of Y satisfying some kind of constraint. Okay, so for example, let's say that we do this. So Z is the set of integers. Okay, and we can have a subset of Z where X is defined to be the set of all elements of the integers such that the following constraint holds. So n is odd. Okay, so this would be the set of odd integers. Okay, but I could also put more constraints. I could also say n is odd and n is between 6 and 1. Okay, so this turns out to be the same as the set 1, 3, and 5. I've just written it in a different way, and it is a subset of the integers. Okay, and the other thing to keep in mind about subsets is that if we have a map from Y to some other set, okay, and if X is a subset of Y, then it's possible to take the map and restrict it to the subset. I'm defining this now. So the restriction of F to X is a map, which I'll call F vertical line X, okay? And F vertical line X, or F restricted to X, goes from X to Z. And the way it works is that it takes an element inside X and sends it to F of X. Okay, so what I'm trying to say here is that you can always take a subset of a set, right? And if you have a map, if someone gave you a map from the original set to somewhere else, then you can always take that map and consider how it acts only on the subset. And this is called a restriction of a map. Okay, it's like turning to a page in an atlas where you're looking at, just a part of the planet Earth surface, right? And so you're restricting your attention to a smaller part of the domain. that smaller part is a subset. Okay, any questions about subsets?
So Gurman Jote has a question.
Go ahead.
Sorry, I had a question from before. I was just wondering in terms of compositions of functions, if there were any conditions that would, well, like such as if one of like f or g, if they're composed, if one of them were surjective or injective, then it would imply the composition of f and g to be surjective or injective. I was wondering if there are any ways to show that is the case, or if that is the case at all.
So of course you might wonder the different properties of maps, like being injective or being bijective, how do they behave under composition? So if I have two surjective maps, if I compose them, is the result surjective? Similarly, if I have two bijective maps and if I compose them, are they bijective? Right? So you can easily show all of those facts, and those, I think, if one doesn't occur in the assignment, then one eventually will. So yeah, it's a good idea to think about how those properties apply, how they correspond to the operations. Okay.
And also, I had one last quick question. It was in terms of the group of creating group or like constructing a group of like like based on the set of bijections.
Yes.
Like from set to itself. I was wondering if there is some way to like also define like a field with that set as well. Like if
we haven't gotten to fields yet. We haven't gotten to fields yet. Okay.
Okay.
Try to stick for the questions. We need to try to stick to the material that I'm presenting at the moment.
Okay.
For the other questions, you should go on Piazza and put them up.
Okay. Sure.
Piazza it seems to be working very well. There's a lot of questions there. So everyone should be consulting Piazza on a regular basis, but you may want to turn off the notifications because it's very annoying.
Okay.
Okay.
Thank you.
Moving on. So is there anyone that has a question about subsets specifically?
So Shuji has a question.
Yeah, go ahead.
I'm sorry, I still has a question for the previous, the things we talked about.
Okay, go ahead.
So I'm also wondering about the composition of a function. I'm wondering when we write h of f of h of g of f. So what's the domain of h of g? Like, is it a subset of?
You're asking, your question is about what is the domain of this?
Yes.
Okay, so if you look at the definition of composition, you see that when f goes from x to y and g goes from y to z, then the composition fg goes from x to z, because you do f first and then g. So the domain, as you can see here, the domain is x and the codomain is z.
Yes. So will that be a subset of the x, or it will just be x?
What does the domain look like here?
It's x.
Yes, that answers your question.
Oh, I see. Thank you.
Yeah. And anyone else?
Yeah, so Deba has a good question.
Okay, go ahead.
Okay, so my question is that when a given subset contains no elements at all, can we still take a restriction, or is the map meaningless because it maps nothing to nothing?
Yeah, it's the empty map. So it would have empty domain, but you could consider it as a map from the empty set to Z. That's possible. You could certainly do that, but it's kind of vacuous. It doesn't contain any information.
But it exists, like the empty set exists.
Yeah, correct.
Okay.
Yeah. We'll get to a point where we understand that a little deeper. But okay, I'm gonna continue, just unless there's something important that I have to address. Okay, so you should be familiar. So this idea of subsets, very useful. And you should be familiar with the basic operations on subsets. Okay, so I just want to say a little bit about subsets. So about subsets. Okay, so I want to say basically a couple of things. So the set of all subsets is called P of X, subsets of X, is called P of X, the power set of X. Okay, so this is a, right, so this is testing your ability to kind of understand the fact that sets themselves can be elements of another set. Okay, so you shouldn't become too confused. So the question is, what is the power set of the set? Let's say let's say RGB. This is a set of 3 letters, and what is its power set? The power set is a set, and what does it contain? It contains all possible subsets. So the simplest subsets are the empty set and the full set RGB. Those are the obvious subsets, which are the smallest and the biggest. But there's a lot of stuff in between. There's the sets that have only one thing in them, the subsets R, G, B, right? And then there's the pairs R and G, R and B, G and B. Okay, and so we see that we have 1, 2, 3, 4, 5, 6, 7, 8 elements, a set of cardinality 8, or in other words, yeah. Okay, so this is a set of sets. It's a set whose elements are sets. And you could take the power set of the power set and so on, right? You could produce a huge number of sets this way by using the power set construction. Okay. And then there's 2 basic operations. On subsets. By the way, the symbol for subset is either given like this as this is usually the containment symbol, and there's usually some people put a line underneath it to indicate that it might be equality. So this is like is a subset, but it might be the whole set, right? It might also be the empty set. So some people don't put that line, and they just say that X is a subset of Y, and this may be an equality. But some people also use this symbol to mean a proper subset, and proper means that the full set is excluded. Proper means that it must be smaller than Y. So just to avoid ambiguity, I prefer to use this. That way you know that it might be the whole set. Okay, so what are the basic operations? Well, the first one is called the union. Union of subsets. And this is what it sounds like. It's putting all the elements of X1 and the elements of X2, right? Putting them together to get a larger subset that contains both of them. Okay, so it's the set of all elements in Y such that X is in X1 or X is in X2. Okay, so in other words, if I have, if this is my set Y, and if this is my set X1, subset X1, and if this is my subset X2, right, then the union would be all these elements, the elements which are in X1 or in X2. Okay, and that's the union. Okay, so you got to be careful that the size of the union may not be the sum of the two sizes, right? Because there might be some elements that are in both X1 and X2, right? So if you counted the elements in X1 and the elements in X2 and you tried to take the sum, you would be double counting the elements which are in both of X1 and X2. And those elements are called the intersection. X1 intersect X2. This is the intersection of subsets. And this is the set of elements in Y such that X is in X1 and X is in X2. Okay, and if I look at my example, this would be the intersection. It would consist of that single element. Okay, and so you can think that that these are operations on subsets of Y, and so in a way, you can say that they're operations on the power set of Y. If you take two elements of the power set, what are they? They're just subsets of Y, like X1 and X2. These are elements of the power set of Y, and this union is another element of the power set of Y. So we see that given two elements of the power set, we have a way of combining them and getting another element in the power set. And similarly here, we have a way of intersecting them and getting another element of the power set. So you could think of these as being operations on the power set, which are binary operations, meaning that they take two inputs and give one output. So both of these are binary, so-called binary operations on the power set of Y. I just wanted to make a comment. This is not, it's just a question of language. Okay. Okay. Any questions about subsets so far?
So, sorry. So Jay has a question.
Go ahead. Go ahead.
Okay. I think I understand. So if we have some set X and there is some function F that maps it to the set Y, and then say there's an inverse function of F called G, which does the opposite, maps the elements of Y to X. So if we wanted to say do a subset of X, right? Well, we just have to restrict the set X to whatever subset, say Z, and then apply the same function F to that, to where it maps those elements to Y. And then because that was already a subset that got mapped to Y, so only some of the elements of X, of the set X got mapped to Y, then it's going to be a smaller image, so as in less elements in Y than if it were.
It could be a smaller image, or it could be the same image.
Or the same. Oh, right. Because it could be the full thing. Right. So in that case, we don't need to make any special restrictions other than the fact that it's a subset. There's no rules that change in our mappings of F and G. Like, I think I'm just...
The restriction, F can be restricted. If you have a map from X to Y, it can be restricted to any subset of X.
Right.
Okay, but notice that I am restricting F to a subset of the domain. I cannot restrict F to a subset of the codomain. That doesn't make any sense.
Right.
I mean,
because it's not from X.
Because F goes in one direction. It takes everything in X and maps it somewhere. And if you restrict your attention to a subset, then it will take all of those things in the subset to Y.
Okay.
Yeah. Anything else? I'll take another question.
Okay, so Zhao Ju has a question.
Go ahead.
Yes, it was also related to restrictions. I was wondering how we attain a restriction, whether that's through applying a function or stating it.
Okay, so if you have a map, everyone wants to call it a function instead of a map because of your high school experience. If you have a map from y to z and you have a subset of y, then the restriction is defined. You see, it takes a point to the value which the function takes at that point. So in order to define a restriction, you just need a map and you need a subset of the domain. And then you get your restriction as given here. Okay, so you cannot restrict if you do not have a map. It's the restriction of what? Of the map. And it's a restriction of the map to a subset. So you need the map and the subset, but once you have those two pieces of information, you got your restriction. Right, so in other words, when we have an election, we're supposed to get a mapping from all voters, eligible voters, to results, to people, preferences. But when we do polls, we restrict our attention to a subset of the population, and we assign the preferences just to that subset. That is called a restriction of the voting map. The restriction of the voting map to a representative subset is a poll, more or less. Okay? Okay, and okay, let me give a few more facts about subsets. So a map, so these were subsets. Actually, let me rename this whole section to subsets because it's really all about subsets. The definition is given there. And here is another definition of the restriction. Okay, so we have the basic operations on subsets. We can take their union and we can take their intersection. Now, there's also a construction of subsets coming from a map of sets. So if I give you now a map of sets, okay, there's a special subset which is called the image. Of F, which has the name do I want to use a notation for this? Let me just check. Let me call it image of F is a subset, is the subset of Y of all, so defined by this. So the image of F is the set of all elements in the codomain such that there exists a point in the domain with f of x equals y. Okay, so it's the all taken values. It's what it is. It's what it sounds like. It's the image. It's all the points that are taken on as values of the map when I apply it to every possible point in the domain. Okay, that image may not be the whole space. It would be the whole space if it was a surjective map, but if it's not surjective, it could be a subset of the codomain. And that subset is called the image of the map. Okay, and and then there's another one which is a bit more tricky, which is the idea of a pre-image. Okay, so if F is a map from X to Y, and we fix a point or an element Y in Y, then its pre-image is the following set. It's denoted in this way. So this is, I'm deliberately, and the whole mathematical community is laughing and trying to trick everyone, because the notation is like this. The notation uses F to the -1, even though F may not have an inverse. So this has nothing to do with inverse. Because the inverse may not exist, okay? But it's used anyway, and this is called the pre-image. It is the set of points in the domain which are sent to Y. So let me just draw a picture. Okay, so suppose that I have a map. Let's not make it surjective. Let's go here. Okay, so we have our map. I defined it on every member of the domain. So I'm done defining the map. Okay, suppose that I was interested. Let me give these names. This is X and this is Y. Okay, and if I fix an element Y, a specific element Y, right? Then the pre-image means that I have to do I have to trace the history of that element. I have to go backwards, right? And I need to follow what the map did and which elements were sent to that element. Okay, and these elements here, this is F inverse of Y. It's those elements in X which are sent to the element that you chose, this special element Y. So this means that this is kind of interesting, because this means that for each element in the codomain, we get a subset F inverse of Y inside X. So this is now what we're seeing here is that once you give me a map, okay, there's a whole bunch of special subsets that are defined by this map. So one special subset, let me give it I don't know, a pink color. So this subset of Y, this is called the image of F. It's all the taken values, the achieved values by the map F. Okay, and the other thing it defines is that for every point, we get a special subset of the domain. For this point, we have this subset, which is the pre-image of Y. For this point, the pre-image would just be a single point. And for this point, the pre-image would be these two. Let me give another example. Suppose that we had this point Z, right? I trace it back and I see that I have that in the pre-image and I have that in the pre-image. So this subset would be F inverse of Z. Okay. So we get a whole bunch of subsets of X, one for each of the points in the codomain, or actually one for each of the points in the image. So maybe I'll even make it more precise. Yeah, for each point in the, actually this is good, yeah. So we have images, and we have one image, and we have a whole bunch of pre-images. Okay. Let's actually continue. Let's continue. So if I look at this point, let me call this W. Oh dear, that's not a good, yeah, that's not a good color. Take this. Suppose this, I call this W. The pre-image of W is here. Let me call this U, and let me call this, so U has pre-image here, F inverse of U. And V has pre-image here, F inverse of V. Okay, and finally, if I give this name T, the pre-image of T is empty. It's the empty subset. Okay, so so now I want you to notice something, which is that every point in the domain is in some preimage, right? This point is in the preimage of Z, and this one is too. Okay, these 2 points are in the preimage of Y. This is in the preimage of W, and so on, right? So, and the other thing you should notice is that the subsets, the preimages, they don't intersect. Right? It's impossible that they would intersect, because you cannot have an intersection between the preimage of Z and Y, right? Because if you did, then that point would be sent to Z and it would be sent to Y, and that's against the law. You cannot have a point which is sent to 2 different images. That's the way that maps are. Maps, take a child and send it to a certain school. You cannot send the child to 2 schools. Okay, so in other words, yeah, you could even think of it that way. You could say that you could think of these as children, right? And these are schools, and no one wants to go to that school. I won't say which school that is. Okay, but these 2 kids are going to this school. These 2 are going to that school, and so on. Okay, so what we get is a division of the set of kids into some subsets. We divide them into groups, right? This is the group of kids going to one school. This is to another. This is to another. Okay, and these groups do not intersect. They have empty intersection. Okay, so what is this kind of division of a set into subsets? Raise your hand. Question. It's a question. I should, if I could do a poll, if I could do a quiz, I would do it on this question. Yes. Sorry. Raise your hand again. Elliot, answer.
I believe it's a partition.
Yeah, it's a partition, because you looked at the assignment.
Yeah.
So a partition is exactly this. A partition is a decomposition of a set into a bunch of subsets which do not intersect. Okay, except that there's an additional constraint that the partition cannot have empty set included. So here what we see is that there's one subset, another, so there's 1, 2, 3, 4, 5 subsets of children, and that gives a partition of size 5 of the set of children. Okay, so what we obtain, this defines a partition of the domain into subsets, and these subsets are labeled by what? What are the subsets? You know, I told you that I divided the children into these groups. So what is the label, the distinguishing label for each of these groups? The answer is that the label is which school they go to. So what are they labeled by? Well, this is labeled by V. This is labeled by, this is labeled by Z. This is labeled by V, etc. So they are labeled by certain elements. And these elements are elements of what? Well, they're elements of Y, but this element is not one of the labels. Okay, because no school goes to no children go to this school. Okay, so the labels are given by the elements of the image. Okay. So this is a standard way of defining a partition on a set, which is to map the set somewhere, to map the set into some other set, and then you're going to get a partition because some of the elements of the domain will be sent to the same point, and those will be grouped together in one subset in the partition. And then all of the elements of the domain will be grouped together into subsets, and each subset is labeled by a point in the image. Okay, so anyway, hopefully, so what I've covered today, just reviewing quickly, is some basic properties of maps. We want to know whether they have certain properties, so we label them with language. So this is just language: injective, surjective, bijective. And then there's the fact that the bijections have a special property that they can, every bijection and every other bijection, they can always be composed, and they always have inverses, and that's in the assignment, and the composition is associative. There's a unit, so it forms a group. Okay, and then we have this idea of subsets and operations on subsets and partitions. We're going to continue with constructions of sets on Thursday. We're just going to finish it up, and then we can hopefully after this week we can move on to the beginning of the vector space material. Okay, that's it. See you on Thursday, and I'll stick around for a little bit, for about 10 minutes or so, for questions.
Okay, so Charlie has a question.
Okay, so like initially I just wanted to say two quick things, but then I also have a question. First, where you have like the f to the -1 z in your little drawing,
yeah,
you wrote x instead of z, which is a little confusing.
Here?
On the left side, yeah. Where you were.
Sorry, that's a Z, sideways Z. Sorry.
Oh.
I write Z with a line through it.
That looks like an X to me.
Yeah, sorry.
No worries. Also, when it comes to the symbol for like sets being contained in, I think.
Yeah.
I was just in Math 138 yesterday, and a teacher mentioned that like some people or some textbooks will use different like definitions for each of the symbols. So like sometimes if you don't have the line below it, it can mean that X is not contained in Y. So I think what he said is just to always like use the line below to indicate that X is contained within Y. And then if you're trying to indicate that X isn't contained in Y, you just put a line like across through the bottom line.
Yeah, there's also this notation. So what he's talking about is putting a line like that. This means that X is a proper subset, meaning that it is a subset, but it is not equal to Y.
Yeah.
Okay.
Okay. And then also just a question about like, sorry, could you go back to like the last page? About like sort of the pre-images and stuff.
Yeah.
So would like, I just, whenever I'm trying to visualize the stuff,
I don't know
think of
why,
it
but
like
it's
as
not
in,
showing me your face. Is that because your video is off?
yeah, my video is off right
Okay.
now.
Okay.
Whenever I think of this stuff, I think like I try and relate it to something I know. So I tried to think of like a parabola. So would, in the X domain, would those points that are within like the partition of Z or whatever, would those be like, because they both sort of are, they correspond to the same value of Y. So would those be the 2 points that end up in the same partition?
So if you fix a point in the codomain, okay, and if you look at the pre-image, what you're looking for is all points in the domain that map to this point. So in other words, you would see that there are 2 points which are mapped to this point. So if I call this Y, this would be X1 and X2, and the pre-image of Y would be the set containing X1 and X2.
Okay, and so that makes up a partition of
Yes, because that's right. So if you just divide it up, so if you choose all possible points in the image, so this would be the image. The image would be all these points, the image of F. Okay, because all of these values are taken, but the highly negative values are not taken by this map. And so if you look at all the pre-images of all these points, right, what are you going to get? Well, for this one, for example, for this one, you're going to get these 2 points and so on. So for every point in the image, I'm going to get a pair of points, except for, of course, except for this point in the minimum, right? That's only going to have 1 point. So what you'll see is that you're going to get one subset, let's say one subset, then you're going to get another subset of 2 elements, then you'll get another subset of 2 elements, and so on. And so you're going to decompose the domain, right, into an infinite number of subsets, each subset having exactly 2 elements.
Except for the first one.
Except for the first one, yeah.
Okay.
Which has only 1 element.
And so that is partitioning the domain.
That's partitioning the domain into an infinite set of subsets. Yeah.
Okay, awesome. Thank you. That clears things up.
Okay, so Kai also has a question.
Go ahead.
Hi, Professor.
Hi.
So I want to know, you just mentioned there are injection, bijection, and surjection of maps.
Yeah.
So is there any maps that is out of those 3 categories?
That are what?
So is there any maps that are nor injection, nor bijection, nor surjection?
Well, what do you think? What do you think?
I think there is, but
So for example, what? How do you produce an example?
Like, for example, let's.
So if we're going to produce an example, you have to decide first what are the domain and codomain. Tell me that. What domain do you want to use for the example?
Just say the domain is 1, 2, 3.
And the codomain?
And the codomain is also 1, 2, 3.
Okay, as you like. Okay.
But
and then where does 1 go?
1 go to 1 and 2 go to 1, 3 go to 1.
Okay, just wait. So 1 goes to 1. Okay. Then the next one you said is you want 2 to go to 1. As soon as you do that, what are you ruining?
I am ruling out injection.
That's right. So it's not an injection.
Yeah.
But I haven't finished defining the map, right?
Yes.
So if I continue
every
the
element in the domain has to be assigned to a element in.
yeah, so I haven't defined the map yet. So the third has to go somewhere. So it could either go here or here,
But
right?
can it
So
go to 1?
and it can go to 1 too, exactly. So you could do this. Okay, this is not injective, and it's definitely not surjective.
So what could it be called?
Just 1 second. And then if I do this, it's also not injective and not surjective. And similarly, if I do this, it's also not injective and not surjective.
Yeah.
Okay, so as soon as you made that choice of ruining injectivity, you were forced basically to fail both. Injective and surjective fail at the same time.
Yeah.
On the other hand, suppose that I let the codomain be just 2 points. So now I have 3 points being mapped to 2 points. Okay.
Yes.
So then
So
the
that's
third point has to
subjective.
be sent somewhere. So there's 2 possibilities. You could either do this. This would be not injective and not surjective. But then this one would be what?
Would be a surjective.
But not injective.
Yeah.
Yeah.
Oh. So you're saying that.
I think you understand.
Yeah.
Okay. Other questions?
Yeah, I do have other questions. So can we say that the image of a map is just the map between domain and range?
So range is just the old-fashioned way of saying image. So range is the same as image.
Oh, okay. All right. And also, so the mapping between pre-image and their image, are they the subset of the map between the domain and the codomain?
I'm trying to interpret your question, but I'm not succeeding. So you just need to think a little bit more about your question. Ask on Piazza. Let's move to someone else, just because I want to give people a chance to ask more questions. So and the other thing is, I don't know whether it's a good idea to require people to have video on when they ask questions, just because then I get a chance to know who you are.
It's
okay. Okay. Good. Okay. So.
Okay.
Any
so
other
G
questions?
Cow?
Yes, I have 3 questions. First, can you move to the notation of the restriction?
Yeah.
I just want to confirm one thing.
Yes.
So the subscript for this vertical line in the middle, shouldn't it be Y rather than X?
No, because the map F has domain Y. Okay. But I'm trying to define a new map.
Oh, that's a subset. Okay.
Which is the restriction of F to the subset. And so
Okay,
that's why I need to put the subset here.
Okay, I understand. So second thing is there any relation between category and group?
Yes. A group is a special kind of category.
Group is a special. Okay.
But don't worry about that at the moment.
And I think you also mentioned something about symmetry. I just get confused there.
Yeah, so symmetry, a symmetry, okay, is a symmetry of an object is a transformation which takes the object to itself. So for example, if you say that a circle is rotationally symmetric, that means that if you rotate it in the plane, it will be a map from the circle to itself. Okay, and that map should be invertible. It should be a bijection. So another example would be if you take the real line, a symmetry of the real line would be taking the real line and shifting it over to the right by a certain amount. That is a map from the real line to itself, which can be inverted. Okay. Another example is to take the real line and just flipping it over, like taking x to minus x. Okay, that is a bijection from the real line to itself. Okay, so whenever you have a set and you have a bijection from the set to itself, you should think of that as a transformation of the set, which sends the set to itself. And that is what's called a symmetry.
So that's synonymous to group?
No. The group is the collection of all possible symmetries.
All possible symmetry. Oh.
So, for example, here we're talking about all possible bijections, right? So here I drew 6 bijections from this set to itself. These are all the possible symmetries of the set of 3 elements. Okay, and this set of all possible symmetries forms a group. It is a group of 6 elements. We can take the elements of this group and we can compose them with each other, and we get a multiplication and so on. So the group is the group of symmetries. The elements of the group are symmetries.
Okay, thank you.
You're welcome.
Okay, so Daniel has a question.
Yeah, hello, sir. So
Hi.
just to be perfectly clear,
Do I have your image
sorry.
here or not?
Hello?
Hi.
Can you see my camera?
Yes.
Sorry, I'm on my phone. So we cannot define a map which takes one element to multiple different, so one X in the domain to multiple elements in the codomain. We don't accept that as a map.
Can you just repeat it? It takes what?
So we can't have a map which takes one element in the domain to multiple elements in the codomain.
That's true. I mean, a map has to, first of all, the map is a system. The map is like a machine. It's a system that operates on all the elements of the domain. It tells you where all the elements of the domain go. It's a certain system, okay? And furthermore, each element of the domain must be sent somewhere, and you cannot somehow split the element and send it to 2 different elements of the codomain. No, a map is like a school system. Every child is sent to a school. Every single child must be sent to one of the schools. You cannot send a child to 2 schools, and you cannot leave a child at home. No child is left behind.
All right, thank you. Yeah.
I mean, there is homeschooling, but I'm going to ignore that for now.
Okay, thank you, sir.
All right, so Kin Yuan has a question.
Yes, hi, Professor.
Hi.
I have a question about the bijection from the set to itself, the bijection x to x. I don't understand the first point. What does that mean that any 2 of them may be composed to give a third, given an associative multiplication? What does associative multiplication means here? I don't really understand that.
Who am I talking to? Are you there? Oh, sorry, I didn't see your mouth. Okay. Good.
Oh, okay.
Okay, so look at this here. Okay, so here we have a map from 3 points to 4 points, and we have a map from 4 points to 2 points. Okay,
Yes.
so I can compose F with G. I can do F first and then G.
Yes.
But I cannot do G first and then F.
Yeah.
So there is no composition. So here, G, F is undefined.
Yes.
Okay. When you're talking about bijections from X to itself, this problem does not occur. Okay, because X is the same here and here and here.
Yes.
It's all X, X, X.
Yeah.
So when I'm talking about bijections from X to itself, that means that the domain and the codomain is always X, 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 X. So that means that I can always compose F with G, G with F, F with H. They're all composable.
Oh, I see.
Okay. So given any 2 of these bijections, I can always compose them.
Yeah, because
Number
their
1.
domain are the same, right?
Okay. And so that means that any 2 can be composed, and the composition is associative because we have the associative law.
Yeah.
Okay, so that means that it's like a number system. Any 2 numbers, you can multiply them and you get another number. So the bijections, they satisfy something like the multiplication on numbers, somewhat similar to that. And that is what is called a group. It's a single binary operation. You take two inputs and one output. Okay, and that operation must be associative. If you have that, and if you have inverses, and if you have an identity element, that kind of structure, that mathematical structure is called a group. So I'm just giving you a very simple type of group. It is the group of bijections from a set to itself.
Okay, I see. I got it. Thank you.
Okay. Okay, that's it. See you on Thursday, everyone. Good class. Make sure that you use Piazza. And for the assignment, I put the link to the assignment on the web page, so everyone should be able to get it, whether you are properly enrolled in Quercus or not. It seems like people are taking forever to get their U of T emails. But anyway, you have access to the assignment. Okay. Bye-bye.